Good afternoon, Trojans. I'm Erica Maldonado Singh, Associate Director of USC Dornsife Alumni Relations. Thank you for joining us for today's Dornsife Dialogue. If you're watching on Zoom, you're welcome to submit a question at any time using the Q&A button at the bottom of your screen. If you have to leave today's discussion early or want to watch or listen again, it will be on our Dornsife Dialogues podcast, available on all of your favorite podcast platforms. And a link to the video will be on the Dornsife Dialogues section of our website. Make sure to follow USC Dornsife on all social channels. Our handle is at USC Dornsife. Now I'll turn it over to the Interim Dean of the USC Dornsife College of Letters, Arts, and Sciences, El-Naggar.
Good afternoon, and thank you, Erica, for the introduction. So it is my privilege today to moderate this session of the Dornsife Dialogues. And I would like to start by welcoming our audience. Attendance and later views of this dialogue series continues to grow thanks to your curiosity and interest in the insight and research of our leading USC Dornsife scholars and alumni. Many know USC as the home of an outstanding education, top-notch student experience, and excellence in athletics. But USC is also an elite research university at the forefront of many fields. And this is especially true in the rapidly moving field of quantum information science and technology. In fact, the Dornsife College of Letters, Arts, and Sciences and the Viterbi School of Engineering recently partnered to kick off a unified quantum initiative as part of the recently announced USC Frontiers of Computing initiative. Now, it's completely understandable if the quantum world makes your head spin. What's up with Schrodinger's cat, superposition, entanglement, and qubits? And what exactly is a quantum computer? Whether you're an aficionado or just quantum curious, we've got your back with two leading experts who I have the privilege of working with as colleagues at USC, Professor Daniel Lidar and Professor Rosa Di Felice. I'll start with a quick introduction. Professor Daniel Lidar holds the Viterbi Professorship in Engineering and is a professor of electrical and computer engineering in the Viterbi School of Engineering and of Chemistry and Physics and Astronomy at the Dornsife College of Letters, Arts, and Sciences. He is the director of the USC Center for Quantum Information Science and Technology and directs the USC IBM Quantum Innovation Center, which provides access to cutting-edge quantum computers for our students and researchers. Daniel is a leading researcher in quantum information processing, focusing on quantum error correction, which is one of the key challenges that must be overcome for quantum computing to make a difference in people's lives. He is the recipient of countless prestigious honors, including a Guggenheim Fellowship, an IEEE Fellowship, and a AAAS Fellowship. He is an author or co-author of more than 130 technical research articles and holds 4 patents. I'd also like to welcome Professor Rosa Di Felice. Rosa is a professor of physics and astronomy and quantitative and computational biology in the Dornsife College of Letters, Arts, and Sciences. Rosa's expertise, amongst many things, is in quantum computing and materials science, with a particular focus on applying quantum computation to challenges in nanoscience and simulations of molecules, which we're going to talk about today. Very recently, just a few weeks ago, in fact, she is part of a team that includes a master's student from the joint program in quantum information science with the Viterbi School of Engineering and the Dornsife College, were recognized as winners of the Quantum Mobility Challenge sponsored by Airbus and BMW. Rosa is an author of more than 120 papers in international peer-reviewed top quality journals. So welcome, Daniel, and welcome, Rosa. I would like to start from the very, very beginning by asking you to explain to our audience, what is quantum computing based on and what makes it so different than regular computing? Daniel, let's start with you, perhaps.
Okay, so quantum computing is based on quantum bits. Those are sometimes known as qubits. A standard bit, which is the fundamental unit of information in your desktop or laptop, can be in 2 states, 0 or 1, as we typically call them. And a quantum bit, a qubit, can be in a superposition of 0 and 1, which is where the famous Schrodinger cat analogy comes into play. We prefer 0 and 1 to dead and alive. And if you take a lot of these qubits together, you get a gigantic superposition. If you have 10 such qubits, you get 2 to the power 10. If you take 100 qubits, you get 2 to the power 100, and so on. Different states that can all be represented simultaneously in a quantum computer. And a quantum computer can do something very interesting and different with this giant superposition. It can, in essence, compute on all of these different numbers simultaneously. So it's as if it's simultaneously evolving 2 to the power 100 or 2 to the power 1000 different numbers simultaneously in order to try to find the answer to some computational problem. And it does so using additional important quantum features, not just this idea of superposition. In addition, there are effects like interference and entanglement and sometimes tunneling, which are all important buzzwords we can delve into, that aid the speed up that we get from quantum computers. And speed up is really the key gain that we get from this massive parallelism that a quantum computer provides.
Is it fair? Most of our audience obviously will be familiar with what a regular computer looks like. And I want to make this a little bit concrete for people. When we talk about a bit that can be a 0 or 1, I think to most people, they have a realization that in their regular everyday computers, this thing is some element inside their computer that is a transistor and so on. Rosa, could you give us a sense when we're talking about a qubit in the case of a quantum computer, what physically are we talking about?
Yes, that's exactly what I wanted to add on top of what Daniel presented pretty well. So again, in classical computers, we have the transistor. In quantum computers, so how do you realize a bit, a qubit, sorry. We do not have a unique technology so far. We have different technologies. So the IBM quantum computers are based on superconducting devices, which are junctions between different superconducting materials operated with electrical pulses and magnetic pulses. But there are alternatives. So alternatives are ion traps, which are ions, which are charged atoms trapped in specific locations and manipulated in these locations with lasers and optical tweezers. It could be neutral atoms, it could be neutral molecules, and it could be topological materials, as Microsoft just announced, for instance. So all these technologies are currently explored. Again, the most advanced currently is the superconducting technologies, but we don't know now if it is the ultimate technology to unravel the power of quantum computers.
So that makes sense. So essentially, the idea is if you need to exploit these features of the quantum world, you have to go to actual quantum things in order to realize your computing. Those could be electrons, could be atoms, could be ions, or features of these systems like superconductivity that allow you to actually take advantage of these weird quantum properties of the world in order to do computing. A question I frequently get asked is, why USC? What is USC's history in this area? And I'm very proud of the fact that USC was hiring faculty and top researchers in this area, I would say well before a quantum computer sort of entered the lives of everyday people, or before they were realized and you could actually buy them in their current forms. Daniel, could you give us a sense of history of when USC started working on quantum computing? What are our strengths in this area?
Yeah, so USC had an effort in quantum computing way before it became very popular and a feature in the media. It started around, I want to say, early 2000s. There were several faculty here that were active in the field, and just to calibrate, the whole field really exploded in the mid-90s when Peter Shor announced the discovery of what is now famously known as Shor's algorithm, an algorithm for breaking RSA public key encryption. It took several years for the community to really pick this up, but at USC, like I said, it took about 5 years for people to start to work on quantum computing here. since Shore's announcement. And then there started a series of hiring of faculty, including myself. I arrived in 2005. Our colleague Todd Brunn was already here and working actively in quantum computing. And then we established our first center, our Center for Quantum Information Science and Technology, shortly thereafter. We've been hiring in this area steadily, and have gotten some of the very top people to come and join us. I would say things took a turn when we started the USC, at the time, USC Lockheed Martin Quantum Computing Center. And that was in 2011. And that's when we got the very first commercial quantum computer that was ever sold. And that's the D-Wave machine. And so USC has been the proud home of the D-Wave quantum annealer, as it's called. Since 2011, we've upgraded it a number of times, and we're still one of the very few research universities in the world, in fact, any beyond universities in the world that have an actual quantum computer on premise available to our researchers here. And then very recently, we joined forces with IBM, and we established the USC IBM Quantum Innovation Center, of which Rosa and I are co-directors. And that gives us access, as you said in your intro, Mo, to the fleet of very powerful modern IBM quantum computers. And so we've had a long history of continuous activity in this area with important results in pretty much the whole spectrum of activity in this field, both theoretical and experimental, and spanning various modalities, qubit modalities of the type that Rosa described, and also many different areas of the theory of quantum computing. And we also have now a master's program that is training the next generation of scientists who are working in this area, alongside, of course, our thriving PhD program.
I wanted to actually ask you about this a little bit. So I'll come in a moment, I'll come to ask you about the kinds of problems and advances that can be accomplished by quantum computing. But before we get there, so here we are now the home to a quantum computer. We now have this agreement with IBM that gives our students access to quantum computers on the cloud. I'd like to get a sense from you of the training that we are providing to students, both on the PhD level and the master's level. Rosa, I know you teach in that program that actually teaches quantum algorithms to students. Can you give us a sense of the skills that you want students to acquire, and also how you think this helps their careers going forward?
Yeah, let me go a little bit broader than my course. Daniel is teaching in the master himself, and he's teaching actually 2 courses. So we have a breadth of courses. Mine in particular is about applications of quantum computing. So I offer as in instructional modules the hardware that is available, the software that is available for different possible realizations of quantum computation. And then we use the IBM quantum devices, and we use the D-Wave quantum annealer to run some programs. So I intentionally designed this course since the very beginning to not necessarily being very deep, but being practical. So at the end, they should get familiar in using the quantum software that is available, at least on these 2 platforms. I also invite them to explore other platforms, but that's not straightforward because some other platforms are commercial, both for software and hardware. So it's marginally doable. The students that we have usually have a background in computer science, engineering, physics, or chemistry, I would say. There's even one student now who has a bachelor in biophysics. And what they need in order to succeed in the master is strong foundation in computation, We mostly give them the foundations in quantum physics within the master itself, because there's, I mean, they start with a course on Introduction to Quantum Information Science, which is about quantum mechanics with the angle of quantum information science. I mean, of course, if they come with more physical knowledge, they can get farther in carrying out practical research projects. If they do not come with that physical background, still they can succeed and get out with the knowledge in the notions of physics that are strictly needed, and some advanced concepts like quantum error correction and even quantum cryptography, because we have some courses in computer science on quantum cryptography. And
let me add to that, if you don't mind, Rosa. So actually, I want to emphasize that some of our early students went on to join the founding pioneering efforts at the likes of Google and IBM, especially at Google. The team that was formed there actually was based entirely out of USC initially. Some of the people that founded the program there got their PhD under my guidance and other faculty here. So we feel that we've contributed really to the founding of this area outside of academia. It's been a wonderful experience to see these people thrive in these companies, and some of them have gone on and started their own startups. And we're very much in contact with these graduates of ours who are making us very proud.
There's not a week that goes by working at a research university like ours where I don't tell people that the biggest joy that we have is watching what our people, what our students, what our trainees do after they leave USC. And you just highlighted an extremely powerful example of that. Here is a technology that is just taking off, that the public is now aware of, that is moving very, very rapidly. And some of the people that are key drivers in this technology essentially were trained here at USC. I wanna zoom out for a second. Imagine you're not a master's or PhD student in science or engineering who's working on quantum hardware or quantum computing or quantum algorithms. Imagine that, like many of our viewers and listeners, you're just wondering, okay, so here's a new computing technology. It is nothing like existing classical computing, nothing like my regular computer, and the technology is rapidly evolving. What difference will it make to my life? Will it just take place of my regular computer? Can it only solve very specific problems? Are they exciting problems that I should care about? I'll put this question in front of both of you.
Yeah. So certainly quantum computers are not going to replace your email program or your web browsing. Although, you know, people have been pessimistic about computing technology in the past and have been proven very wrong. So I say that with some humility, but I'm fairly confident that's not where the power of quantum computing is going to be. Rather, quantum computing is about solving very hard problems, computational problems, much more efficiently than is possible classically. And we know of several application areas that are going to change people's lives, where this is quite likely to come true. And the first of these has to do with what we call quantum simulation. So quantum simulation is the idea that you need to simulate a quantum system somehow efficiently. And Feynman, the famous physicist, originally thought of the idea of quantum computing already in the 80s, in fact, with this in mind. So the idea that it's really hard to simulate quantum mechanics itself using ordinary, what we call classical computers, your laptop, your desktop, but that if you had a quantum computer you could program, it could do the simulation of a quantum system much more efficiently, exponentially more efficiently. And the reason I say that this is going to have an impact on people's lives is because while it might sound esoteric to simulate quantum mechanics, it actually has dramatic implications in areas such as materials science research, the pharmaceutical world of looking for new drugs. Those are two key application areas. And why is that? It's, well, new materials or new pharmaceuticals. To discover them, you could do something extremely hard, which is to go and build them in the lab, and it's very costly. You can do something else that's very hard. That is, you can try to simulate them on a classical computer. But because these are fundamentally quantum processes that need to be simulated to discover new materials, to find new pharmaceuticals, the best thing you can do is to simulate them on a quantum computer. And this is where there's a tremendous amount of excitement right now and innovation and promise. And we think that we soon-ish, it's hard to give a precise timeline, but let's say it's maybe 5 to 10 years away, we'll be able to actually crack some really hard problems in these areas. And maybe we'll discover something as revolutionary as a room temperature superconductor. I mean, that would just dramatically change the world if we could have room temperature superconductors. By room temperature, really what I mean is, it's a technical term. What I mean is superconductors operate at ordinary, not super cold outer space type temperatures, but in ordinary circumstances. And if you had a room temperature superconductor like that, you could imagine frictionless power transport, for example, which would just be amazing in terms of the energy economy. Or you could imagine building maglev trains or even maglev roads where cars are floating frictionlessly. And so dramatic cost reductions in energy associated with transportation. Likewise, if we could develop pharmaceuticals from scratch very efficiently on a quantum computer, then you can imagine a new world of discovery of new drugs that could fight diseases. All of these things are within realistic reach of the quantum computing revolution.
So thank you for making that very clear, Daniel, that very clear distinction that when we tell people quantum computers are very good at solving or simulating quantum systems, this is actually people's lives, right? Drug discovery can be a quantum problem. The discovery of the next solar panel material that goes on people's homes is a quantum problem. The discovery of a superconductor is a quantum problem. So here you heard it, folks. If people say quantum computers are very good at simulating quantum systems, we are talking about things that impact our everyday lives. I want to bring up a couple of very concrete examples, since we are talking about simulations. Actually, so Rosa, this is for you. You recently won an award, this Quantum Mobility Challenge, for doing quantum simulations. Tell us a little bit about that project, and please jump in and tell us anything else that you have on your mind about simulation of quantum systems.
Yeah, okay, thanks, Mo, and sorry for interrupting. Let me first comment on the discovery of the room temperature superconductors, and then I'll get to the transportation industry. So discovering, I mean, I told you earlier that the chips that realize qubits are built with superconducting materials. And those superconducting materials nowadays, they have to be refrigerated to very, very low temperatures, which make the process very costly. So finding room temperature superconductors would also impact the sustainability of quantum computers themselves. Now, coming to your hint about the transportation industry. So in the transportation industry, one problem, one fundamental problem is corrosion. One practical problem, sorry, not fundamental, is corrosion, because materials, I mean, the surfaces of aeromobiles and cars are formed by aluminum alloys that undergo corrosion when exposed to ambient or also by friction with other materials in the components of a car. Now, how do we prevent corrosion? Corrosion is bad. It can be dangerous for the operation, and it's costly because the cars have to be replaced and the aeromobiles have to be replaced very often. So how do we prevent it? With coatings. And coatings are normally formed by molecules. Now, these molecules have to bind pretty strongly to the surfaces of the aluminum alloys in order to create a stable film. And that means reorganizing the electrons in the molecules when they are absorbed on the surface. This is a quantum problem. And if we can map it on a quantum computer, then we can predict the energies potentially with a very high precision, which is needed to translate the science to technology industrial level. Now, what we did in the challenge is to demonstrate a protocol that uses quantum computation as an edge technology to predict binding energies for these systems. The protocol goes all the way from database analysis for molecules and materials, from classical computation, from a bridge between classical and quantum computation, and then quantum computation using the IBM devices and the IonQ AWS Amazon Braket devices that were made available to us within the challenge from the organizers and sponsors. I'm continuing to work on this project. I liked it, and there's a lot more to do at the, I mean, in terms of algorithm development and theoretical foundations, in addition to running.
So it's clear that there's a lot of movement in developing new hardware. It is clear that there's a lot of movement in new algorithms. It is also clear to people now that these problems are ones that do affect people's lives. So then the natural question that would then come up is, what's the hurdle? What is the thing that needs to be solved in order for quantum computing to fulfill this promise?
Yeah, so this brings us to why you, Mo, are not sitting simultaneously where you are and at the back of your room there on this other chair. In other words, why are you not in a superposition?
Why am I
now?
not the cat? Right?
Why are you not the cat? Why isn't any of us the Schrodinger's cat right now? And the reason for that is the same reason that it's so fiendishly hard to build scalable quantum computers. It's something called decoherence. It's a phenomenon, a natural phenomenon, which, to use another technical term, collapses the superposition of quantum states. And basically, it's this, that every time a quantum entity of some sort, be it an electron or a larger object like a molecule or presumably even a cat, enters into a superposition state, as soon as there is an interaction with the environment, and the environment is basically anything external to this quantum object, that interaction causes superpositions to collapse very quickly, and they collapse into one of, let's say there are just two possibilities, then you would get one of these two possibilities perfectly at random. And so if you now try to build a quantum computer out of qubits, and each of these qubits is collapsing at random because of interactions with the environment into one of its two states, 0 or 1, it's no longer 0 and 1, but it's random, then basically what you're going to get is a computer that spits out random answers, which typically is pretty useless, right? And so to prevent that from happening, we have to work very hard on two separate problems. One is just to engineer the heck out of it and make it as isolated as possible, the computer that is, from the environment, so that it, it's perfectly in vacuum and shielded from electromagnetic radiation and so on and so on. And at the same time, we still need to access this computer, right? I mean, we still need to input information, let it do its thing, and then output information and read the information. So the fact that we have to input and read out means that we have to open this shield that we built around our quantum computer. And by the way, we also have to control it while it's executing tasks. We have to send in, programming instructions, essentially. So at every level, we're trying to do two things that are contradictory. We're trying to both completely isolate the quantum computer from its environment to prevent superpositions from collapsing, and yet we're also trying to interact with this device. And those two contradictory conditions create this conflict, which makes it very hard to build quantum computers. But fortunately, and this is really where USC has been at the forefront since the very beginning, we have ways of dealing with this problem, and that is known as quantum error correction. And so quantum error correction is the idea that we can try to be clever and do stuff, which we can get into, that despite these contradictory requirements that I just described, despite this, we can still input, control, and output information reliably by correcting errors and the error is the collapse of the superposition, essentially correcting errors either while they're occurring or after they've already occurred, or maybe we don't even need to fully correct these errors. Maybe we can just suppress the errors and sort of prevent them from rearing their ugly head before it's too late.
And how far along are we in overcoming this challenge?
Rosa, you want to take that?
Well, I mean, again, at USC, we have a lot of expertise in this, and so there is progress. I cannot quantify how far along we are, but definitely there are steps that, I mean, imply sophisticated treatment of the quantum states to do that at the software level. At the same time, there are efforts at the hardware level to improve the technology. Now, it's not only at USC. No, we just saw the announcement by Microsoft of their topological chip. And that's something that is supposed to realize implicitly quantum error correction. Now, I haven't looked at the details of the article, and I don't know at which level this is realized in this first quantum chip. I think it's only a prototype, conceptual prototype, that doesn't really do that. But I mean, there is a critical mass of people working in that direction, in both physics, engineering, and computer science. And I would say in the last 10 years, the progress has been gigantic. So I'm hopeful that in the next 5 to 10 years, I would say we will have some logical quantum computer that can solve our problems.
It's clear that there's big efforts going on across both industry and many universities, including USC, to tackle these problems, right? For example, to solve this fundamental, or at least to mitigate this fundamental challenge of error correction. But in the meantime, we're also seeing a lot of very clever teams, including you, come up with some solutions to show utility for quantum computing with the current state of technology. And a question that I often get asked is, earlier we talked about applications of quantum computing to simulating quantum systems. A question that I often get asked is application of quantum computing to the life sciences, to the health sciences, to people's lives, literally, right? To people's bodies. And I wanted to ask both of you about your efforts in this area, because Daniel, I know you've been involved in the application of quantum computing in the wake of COVID-19 disease. And Rosa, I know that you and Daniel and the chair of our quantitative and computational biology department, Rima Rose, were one of the first teams to basically put together a demonstration of quantum computing for simulating a biological problem. So I want to hear, I think this would be very interesting for our audience. So I want to hear from both of you about your efforts in this area. Daniel, maybe let's start with you about the COVID story.
Yeah. That's right. So in the early days of COVID, I felt I wanted to do something other than just staying home, and it happened that I had a collaborator who was a real doctor working on infectious diseases, and he was able to get data from a French hospital where there were patients who were being classified into either having a severe reaction to COVID or moderate reaction to COVID or no reaction to COVID at all. And using that data, we built a machine learning model that was trying to identify what the genetic underlying cause was for this severe versus moderate versus no reaction. In other words, is there a gene that's responsible for severe respiratory reaction to COVID? And we were able to do that using both classical machine learning models and a quantum machine learning model that we built. And the quantum machine learning model, we ran it on the D-Wave machine that we have here at USC. And a combination of these classical and quantum machine learning models that were basically playing off against each other, reinforcing each other, checking each other's answers, was able to actually find the gene. This was in the early days, and of course the virus has mutated many times since. But nevertheless, a particular gene was identified, and I left the project, but I know that our collaborators then went on and pursued designing a pharmaceutical treatment that would be based on this gene discovery.
And Rosa, I wanted to also ask you about your efforts and simulations of biological problems using quantum computers.
Yeah, thank you, Mo. So I'm starting slowly to work on drug design, and sorry, that Daniel mentioned earlier. And again, this is a quantum problem because in drug design, we look at the formation of complexes between small molecules that are the drugs or ligands and proteins that carry out some functions in the cell. And these functions are unbalanced and then the disease arises. So there is a reorganization of the atoms and the associated electrons when this complex is formed with respect to the isolated components. And this is an issue of characterizing the binding energy and finding the most favorable complex. And how it is formed can give us a tool to develop industrial process to produce the drug. So I'm starting to target cancer drug design, where drugs can bind to either proteins or nucleic acids. And the idea is exactly that. So to characterize the energies, and we need development at many different levels, at the classical level, at creating a bridge between the classical output and the quantum input, and then running on the quantum input with novel algorithms, potentially more powerful than the ones that we are using now, and potentially taking advantage of quantum error correction if doable. There is another problem that really attracts my attention, and it's in my plans, which is DNA replication. So there is a hypothesis that DNA replication involves electron transfer in nucleic acids and between proteins and nucleic acids. Electrons are quantum particles, and we can only describe them with quantum physics. The quantum systems that are at play in this problem are huge, unaffordable on classical computers. So either we have quantum computers or we do not tackle the problem with an accuracy that will tell us the mechanisms. So that's really about discovering the mechanisms for DNA replication, which I find fascinating.
Terrific. So before we turn to some of the great questions that we're already getting from the audience, and also some of the questions that we got beforehand from registrations, I want to pause here for a second to tell our audience that USC is now home to this quantum initiative that is part of the Frontiers of Computing effort that's going on in the whole university. And our initiative is designed to essentially tackle both the fundamental problems that will get quantum computing to make a difference in people's lives, like quantum error correction, develop new quantum technologies like quantum sensing, but also give our students access to quantum computers, both as you see on your screen, the D-Wave system that is housed here at USC at the Information Sciences Institute, and cloud access to all of these quantum computers that IBM is host through our USC IBM Quantum Innovation Center that Rosa and Daniel are the co-directors of. And at the same time, we're interested in having our students and our star faculty and postdocs and PhD students work on leveraging these quantum systems to do all these kinds of simulations that we've been talking about for problems that range from energy material discovery and drug discovery. So USC is really, really well positioned for these advances that are happening in the quantum computing and generally the quantum information science world. All right, so I would like to turn my attention to some of the questions that we've gotten either from registrations beforehand or right now coming in from the audience. And I'd like to start with a very general question that arrived about whether we see that the biggest challenges in quantum computing require more practical experimentation or more theory development. Daniel.
Well, it's both, of course. We need advances on both the practical side, experimentation side, and the theory side. They go hand in hand. They feed off of each other. And I would say that the most significant efforts happening currently at, let's say, the leading commercial labs like Google and IBM and others have large teams of both theoreticians and experimentalists. And of course, these teams are being fed from institutions like USC, as we discussed before. So it's both.
Yeah. And sometimes, can I add something more? I mean, sometimes, the kind of theory that we need to go hand in hand with the experiment is not necessarily something that directly interprets the experiments or guides the experiments. It could be just more fundamental and predict transformative concepts that may, create that step that is really needed.
We also got a few variations of the same question, which is, I think it's not only talking about college students, it's asking, how would someone get involved? What should students study? How would they prepare for if they're interested in a field like this?
Yeah, if you have a good background in math or in physics or in computer science or in chemistry, I would say any one of these, or in engineering, any one of these is an excellent entry point. Quantum computing or quantum information science is very broad. We accept students into our master's and PhD programs with all of the above type backgrounds. And I mean just one of the categories that I listed. You don't have to be an expert in everything. And then we bring everybody up to speed. So there's many different entry points, and you don't have to be a super specialist in quantum computing in order to get started as a researcher.
Yeah, I also want to mention, sorry, Ma, need or plus for interdisciplinary research. So a person, a student, a researcher who has, different facets, different expertise is also something that is promising towards progress.
Terrific. We got a question asking us to say something to our audience about news that made big splash this week from Microsoft, reporting what appears to be a significant development in topological quantum computing. Daniel, can you narrate that a little bit for our audience, help maybe explain the background for that and why that may be another big promising technology for quantum computing?
Yeah, so we talked about quantum error correction before and the fragility of qubits and so on. And for a couple of decades now, this beautiful idea has been guiding theory and experiment that's related to topology. And we're not going to get into topology right now in any depth, but basically the idea is that you can build qubits that are very, very robust. It's really hard to break them, and it's the topological feature that they exhibit which makes them so hard to break. And when I say break, I mean the environment can't break them. It can't break the superposition. So Microsoft is one of the leading research labs where people have been trying to build these super robust so-called topological qubits. They've been doing that for more than a decade now. And the paper that they published in Nature just a few days ago is a progress report on being able to measure these topological qubits if somebody actually were to make them. Right, so essentially they presented a device that could tell you, yeah, aha, this is a topological qubit. It's called a Majorana zero mode is the technical term. It's a piece of wire with, in essence, two halves of an electron on either end. It's an exotic thing, right? I mean, breaking up an electron into two Majoranas, two halves, so to speak. So you can see that this is very advanced technology. They didn't actually report the discovery of the Majorana zero mode itself. They didn't report on a topological qubit as such, but they reported on a device that would be able to measure them if they actually existed.
We didn't talk too much about the implications of quantum computing for cryptography in this conversation. But we got a really wonderful question from one of our audience members, Charles. So Charles is asking, once quantum computers are more accessible to the general public, would existing cryptography methods become ineffective or even obsolete? Would the entire field of cryptography need to restructure?
Happy to take it, or Rosa, if you prefer.
Few words, but you're more the expert in this field, so it's I mean, it is already happening. So there's something that is called post-quantum cryptography, which is already a very lively research field in computer science. And we have international connections also to do that. So post-quantum cryptography is realizing some classical methods that can elude the quantum breaking. That's what I understand. Daniel, maybe you can add something.
Yeah, no, I think you nailed kind of the end of the story, right? So when Shor discovered his algorithm, the reason that there was so much excitement about quantum computing that right after that was because people immediately realized that, wow, public key encryption is no longer safe, and whoever gets
let's pause on that for a second, Daniel. Could you explain to people what was the connection of the Shor algorithm to cryptography, meaning the importance of prime numbers? How are people's information actually, when they're using their everyday computers, are encrypted? Maybe that will set the stage for explaining why then this became a serious conversation.
Yeah, there is an algorithm that is called RSA, and the A is Len Adelman, who is a faculty member here at USC. And that algorithm has basically powered the encryption methods that we use for commercial transactions online, and also various government agencies use it to encrypt their data and so on. The RSA algorithm has really been the foundational building block of encryption methods for decades now. And it's based on a simple mathematical fact, which is that it's really hard to find the prime factors of a large number. And so if you wanted to factor a small number like 15, you could instantly say, oh, 15 is 5 times 3. Those are the two prime factors of 15. But if somebody gave you a number that was 15 digits long or 2,000 digits long, it becomes exponentially hard, essentially, to solve this problem on a classical computer, as far as we know. By the way, we don't know for sure that it's actually hard to factor large integers on a classical computer. But public knowledge about this is that it's a very, very hard task. And then along comes Shor in 95 or 94 and invents this quantum algorithm for factoring, which would crack this problem in much, much less time, in so-called polynomial time. And that meant that all these encryption methods based on RSA would immediately no longer become secure. And it set the stage for this race to build quantum computers. And then now fast forward to what Rosa was just talking about. Security agencies around the world realize that maybe we need to replace RSA with methods that are robust against these quantum attacks. This is called post-quantum encryption. And so quantum computing has already had enormous impact in this sense, even without anybody having ever built a quantum computer. The very notion that such a quantum computer might arise one day, or maybe already exists in some obscure basement, and nobody knows about it outside of the particular agency that built it, that has set off this race to replace existing encryption methods with post-quantum cryptography. And every encryption system that we have currently is eventually going to have to be replaced at great cost, by the way. So there's already been this impact of quantum computing.
So that's another way that it may affect people's lives
Yes.
very soon, right? In the cryptography area.
Right.
Rosa, we got a question from another one of our audience members, Sumit, who is asking a very interesting question, maybe relevant to your work in simulations, which is about how do you verify the solution? How do you verify a quantum solution or the outcome of a computation on a quantum computing? How do we know that the answer is correct? That's a really fascinating and excellent question.
Yeah, that actually, I noted that question and I wanted to answer. So thanks for pointing it out. So we build benchmarks, at least in what I do in applications of quantum computing. So we build benchmarks on systems that are affordable computationally, both on classical computers and quantum computers. So we test the algorithm, the new quantum algorithm, on the classical data for the systems that we can study classically. And then we project the validity of the algorithm to systems that we cannot treat classically, but have the same chemical nature. So we can expect that they behave similarly. And there is a big quantum benchmarking program that has been run by DARPA, the agency, in the last 3 years, and they will continue. And USC has been part of it with a large team in collaboration with other universities. And I mean, it's interesting that USC was the only academic team in this program. So all the others were mostly heavily company oriented with some academies in the partnership, but USC was mostly academic. So we learned a lot from that, but definitely benchmarking are needed. And we also, I mean, we take inspiration for these benchmarking tests from classical benchmarking initiatives that are already assessed.
Perfect. We got an interesting question that reflects how, what comes into people's minds as they think about quantum computing is probably another advance that is happening very quickly right now, which is the fast rise of artificial intelligence and machine learning. So we have a very interesting question from Josie from our audience asking, do you foresee advancements in AI going hand in hand with quantum computing research and accelerating the field? Daniel, you already actually said something interesting earlier about your own development of quantum machine learning algorithms. So there's already kind of a hint for our audience about a connection that is emerging right now between quantum computing on one hand and the machine learning and general artificial intelligence on the other. Could you tell us a little bit about how you see this playing out in the future?
Yeah, so quantum machine learning is one of those areas that people are working on very hard, and there's some promise there as well. It's not just quantum simulation, which we discussed in detail. There are strong indications that we might get a quantum advantage in quantum machine learning, that is the ability to perform computations better, faster than with traditional classical machine learning. And I'd say there's a kind of a two-way street here between traditional AI and quantum computing and quantum machine learning. So on the one hand, we researchers in this area of quantum information have, of course, picked up these amazing tools that are now available through the likes of OpenAI and other companies that are making these large language models. These have become ubiquitous research tools, and they help us solve our research problems. And we're not unique in that sense. Now, where there is something interesting that specifically about quantum computing in this area is that probably everybody has heard about the fact that the world of AI is running out of data to train on. So where are they going to get new data? Well, I mean, there are also ideas out there, but one of the rich sources of untapped data is the quantum world itself. So you can imagine quantum computers generating an enormous amount of new data that would be inaccessible through ordinary classical computing because, well, we need quantum computers to generate this data. And this could be genuine quantum data. So superposition states, essentially, entangled states. Or it could be data that is classical data, but comes from solving these problems that only quantum computers can ultimately solve. So I think there's a very interesting direction here to be pursued where quantum computers will become the new data farms for classical AI and will generate all this new fascinating data that they could trade on.
Can I
Yeah,
just
please go ahead, Rosa.
on something just to connect to what we have already said? I mean, in the problem of computational drug discovery, for instance, there could be interplay between the quantum computation of energies and the screening of molecule of drugs by artificial intelligence, even classical artificial intelligence. So again, interplay between classical and quantum. And there's a team at USC who is collaborating with the Keck Medical School on image recognition with quantum algorithms, quantum machine learning algorithms. And I mean, I saw the results on tumors. They're pretty amazing.
Great. So we are getting close to the hour mark here, and I wanted to just have you both reflect for me for a little bit on where do you think this is headed in the short term, let's say in the next 5 to 10 years. What do you think the big advances will be? Will there be winning qubit technologies? Will be specific applications that perhaps make an impact on people's lives before others? What excites you about the next few years?
All of these, sorry, all of these. So, I mean, I'm excited by applications, but I'm also excited more by fundamental science. So I'm hoping to see some transformative steps that will give us the ultimate computational technology. And I'm also looking forward to see our young researchers mature and become the creative minds to suggest new steps. That's it.
Daniel, I'll leave you with the last word here.
Yeah, so I think that we're going to come full circle and that, Feynman's original vision of quantum simulation being done by quantum computers is going to happen. And that is where this field is clear to headed. And we're going to, what I'm excited about is, having been involved in this field for, I can't believe I'm saying this, but almost 30 years myself, I think that we're within my lifetime, hopefully I'll live another 5 years or 10 years to see this. We're going to see quantum simulation actually becoming a reality and discovering new things that we're not able to see with ordinary classical computing technology. We're going to discover new materials. We're going to discover new pharmaceuticals. We're going to discover new phases of matter. Maybe we'll solve problems in astronomy and cosmology and particle physics using quantum computers. I think that's where we're going to see the most dramatic immediate impact in the near future. And once that happens, once we have these actual new discoveries using quantum computers, it's going to transform computing as we know it.
Wonderful, thank you. So we are at the hour mark, so it's time to wrap up. I'd like to end, as I started, by thanking both Professor Daniel Lidar and Professor Rosa Di Felice for participating today. If you're interested in learning more about the USC Dornsife's and the Viterbi School of Engineering efforts as part of the Quantum Initiative of USC, please visit quantum.usc.edu that describes a lot of the activity that we described to you today, or go to dornsife.usc.edu for a more in-depth story. Thank you all, and see you next time in the Dornsife Dialogues.